3, 2, 1, let's start. So today we will study, so it's the first lecture of group theory, and in this lecture I'll give you a lot of ideas so that only after this first lecture you will be able to study books of group theory of any complicated level. So why are we studying group theory? Now the interesting thing is that many physical systems, they possess symmetry. Okay, so I'll give you one example from quantum field theory. So consider a Lagrangian density of a Dirac field. So you have psi prime I gamma mu del mu minus m psi. Okay. Now the idea is I'll show that this Lagrangian density is invariant under a certain transformation. So if I make a transformation, if this is my psi, and I'll change the psi to psi e to the power I theta. Okay, so such kind of transformation has a name. It's called as a global U1 phase transformation. Now I'll explain everything bit by bit. What does this mean? But let's check that this is correct. Okay, let's give a quick check in a different color. Okay, just assume a Lagrangian density in terms of this psi bar prime I gamma mu del mu minus m psi prime. And then what we do is we change the psi of and let psi of prime is related to psi of x in this way. So e to the power I theta psi of x, and this you have to do a short calculation, and you will get it like this. So you'll get psi bar of x here and e to the power minus I theta. Okay, maybe I made a mistake. This is e to the power I theta, and then maybe somewhere around here, yeah, so it will be minus I theta. Okay. What we can do now is we can check that if we substitute it in the above Lagrangian density, then on this side we'll have psi bar of x e to the power minus I theta, and whatever is there in the bracket, it remains. And this side we have e to the power I theta psi of x, right? So both the e to the power minus I theta and plus I theta cancels, and we have psi bar of x, and what was there in the bracket, I gamma mu del mu minus m psi of x. We regain the, so the form of the Lagrangian is same under this transformation. Okay, so this is how beautiful symmetry is. So you are studying a particular physical system, you find the symmetries under which the physical system remains invariant, and this give a lot of idea about developing new theories out of existing theory just by looking at symmetries. Now what else we can do? Let me emphasize on this. What do you mean by U1? Okay, now U1 means, so any element G, if it belongs to U1, so U1 is a group, and as a group is a set of elements. So whenever I say U1, you should think of it as something like this. So there is U1, and U1 is a set, and it contains lot of elements G1, G2, lot of elements. So what are the properties of the elements in U1? So if you have G belongs to U1, then you will see that if you do G dagger G, you should get 1. So all the elements that belongs to U1 should be of this form. So this G dagger G is equals to 1 is basically the U. So U means unitary. U means unitary. Now what does the 1 mean here? The 1 here means the representation should be one dimensional. So as you can see, if I write e to the power I theta belongs to U1, then yes, e to the power I theta is an element, which is, as you can see, is a one-dimensional element, and it belongs to a group U1, and it satisfies e to the power I theta. If you do the dagger, you'll get a minus sign, and then e to the power I theta is equals to 1. Okay, so you can mute on your sides. So I think now it's clear. When I write U1, what does it mean? Okay, so if I change the notation, for example, if I start writing G L 2, okay, what does it mean? These two would indicate the dimension, and this GL will tell you something about what kind of elements are there in this set. I mean, what kind of elements and what properties they satisfy. What kind of
Please announce yourself.
unitary. So remember, in quantum mechanics we use unitary operators, and we say that if U dagger U is equals to 1, then the operator U is said to be unitary in quantum mechanics.
Yes, I remember. Okay.
That's it. So U means any element that belongs to the group U. It means the element should be unitary. That's it. They should satisfy this particular relation. Okay. Okay. Now, next is let me tell you something very interesting. Symmetries are very interesting. For example, let's write a QED Lagrangian. Okay. So if you write QED Lagrangian, then the Lagrangian is equal to minus 1 by 4 f mu nu. So this is the Maxwell part, and this is I psi bar gamma mu del mu plus I e a mu multiplied with psi and a minus m psi bar psi. So this is the Lagrangian for QED. And it's very interesting. You see that this kind of Lagrangian is also invariant under certain transformations. Okay, let's look at the transformations. Psi prime x is equals to e to the power minus I theta. Now theta is a function of x. This is very interesting. Now theta becomes a function of x and psi of x. Previously our theta was not a function of x, but now it is. From here you can calculate what psi prime of x is gonna look. This calculation is easy. And then you need also to transform the vector potential, the components of vector potential. They should transform like this: a mu of x plus 1 by e del mu theta. And remember, theta is a function of x. So what I want to tell you is that you have certain physical systems described by Lagrangians, and there are certain symmetries related to these Lagrangians. Okay, so any doubt till now?
No.
Both of you?
Sir?
Okay.
In that wave functions, what kind of wave function we are considering? Is it a complex?
Yeah, these are complex.
Yeah.
Okay.
Okay.
So let's go to next part. Let's go to the formal definition of group now. Okay, so the idea is clear, right? Why we are studying groups. The idea is clear. Okay, and there is one more interesting thing I would like to mention here before we move on. Remember the element that belonged to U1. So it was this kind of group are called as the property of such kind of group are such that they are continuous. So for example, if you vary the parameter theta, the elements will change because the elements were e to the power I theta. So if you change theta, you will go to a different element. So if you change theta by any amount and you are going to a different element, how many elements are there in U1? Any guesses? There will be almost infinite amount of elements because that's why it is called as continuous group. So they will have infinite amount of elements depending upon how you change the parameter theta. Such kind of group have a name. They are called as Lie groups. And Lie groups are continuous groups. Now I'm going to write a concrete definition of Lie group, and then all along the way we will understand them. So let me write. So a Lie group. So Lie groups are smooth manifold. So we will understand what do you mean by smooth manifold as we go along the class. Are smooth manifold endowed with a group structure. Endowed with a group structure. Okay, so what did we learn? This kind of group, they contain infinite amount of elements. Okay, and they can be further classified depending upon whether they are compact, so whether the group is compact or non-compact. Okay, we will understand this along the way. So what is the upshot? The upshot is that when I'm talking about a group, I'm talking about a set of elements. So group is a set which contains certain elements. If it contains infinite number of elements, then it can be like a Lie group. And what if it contains finite number of elements? Then we call them a discrete group. So if you have finite number of elements, then we call them group which are discrete in nature. So I should write discrete group. But you say that, but you will ask a question, can any set be a group? No. A set of elements, we can give them the status of a group only if they satisfy certain conditions. So let us see what conditions they need to satisfy. Okay, so what did I say? So is a group is a set of elements, so you should write it as a set, and it contains elements, so you put some elements. So let GA be an element, GB be an element, and dot 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 dot. If there are infinitely many elements, then they come under the category of Lie group. If there are finite elements, then they come under the category of discrete group. Now, formal definition of group, let me put it here. Okay, take a quick reading of this definition of group. So it should follow the following properties. Closure property. It says that the product of two elements of the group should also be there in the group. So that means that my set G should be such that if I take any two elements, GA and GB, and when I multiply them I get GC, then by closure property this element GC should also be there in the group G. This is the closure property. Similarly, there is associative property, identity property, and inverse. Identity means there should be an element such that when you multiply the element with that element, you get the element back. So for example, so consider there is an identity element E. If you multiply an element with this, you get the same element back. Similarly, there should be an inverse. Okay, so inverse, every element should have its inverse element such that when you multiply them, you should get identity. And we all know what associativity looks. So I think I have one more definition I can put here. The mathematics of group theory. Let me put it below. Okay, so I think, yeah, you can look here, the mathematics. Okay, so a quick look. This is closure property. This is associativity property. This one talks about the existence of an identity element, which is E. Okay, so as you see, when you multiply any element with E, you get the same element back here. And then the last one talks about an inverse. So every group element should have inverse. There is one more thing. A group is called an abelian group if all the elements satisfy this property. Take any two elements, GA, GB, multiply them, and if it is equal to GB and GA, so if it is like this, then we say that the group is an abelian group. Now all the elements, if they should satisfy this property, or I can write it in another way, that GA comma GB commutator should be 0. So if all the elements follow this, we say it's an abelian group. Okay, let's look at an example of a discrete group. Okay, any doubt till here?
No.
No. So let us look at an example of a
Here we should say group means if we multiply this element of this group, then you said that okay, if this result is the resulting element is within that group, within that set, then we say that it is okay, closure properties. But here this group is under multiplications, right?
Yes,
I mean there can be groups which must satisfy under other like
yes, very good.
additions and subtractions like that.
So, yes. For example, you know the real number R.
Yes.
The real number line R. It is also a group under a particular operation. So one particular operation is addition. So you have to define under what operation the set of element is a group. So previously the operation was multiplication, because I was multiplying two elements and I was saying something that there will be a third element, it should belong to the group, and this was the operation, multiplication. If I say that some set is a group under addition, then I should have this GA and GB should be GC and it belongs to G. So, and the interesting thing is these properties can be anything, anything, not just multiplication and addition. There can be some weird abstract combination of elements, and you can form a set which becomes a group under such weird operation. Okay, we will go to that weird operation later on. But now I want to say something about a discrete group. So let me remove all this. Okay, if you look at this equilateral triangle, my question is, under what operations this equilateral triangle will remain same? For example, Yeah, one is reflection around this one.
Yeah,
So
and
if you look
rotation.
at this one, yeah, if I
Rotation.
reflect around this, yeah, and there is a rotation, yeah. So how many reflections? You can see 3 reflections, sigma, sigma prime, sigma double prime. One rotation along anti-clockwise direction, which is looks like R, and another rotation in the clockwise direction, which is W. So what are the group of elements under which this equilateral triangle looks same? So there is a rotation, 2 rotations, clockwise, anti-clockwise. There should be an identity and 3 reflections, sigma, sigma prime, sigma double prime. Now look at this carefully. Here the elements of the group, let me name it. So let this be C3V. So this is what it was written in the book. So this is the name of the group, C3V. So all the elements in the group, if you can look at them, they are nothing but operators. Operators. Previously I said G were the element of the group when I was discussing about the group. But now if you look at it, all the elements of the group are operators because they operate on the equilateral triangle, and we look at the result. So you can also have a group of operators. So the element which was abstract when I was discussing a little bit earlier, now the elements has been given a status of operators. Okay, so
Excuse me.
mhm.
We put rotation and reflection in one group.
Yes,
I thought we
because
should have different groups, one for reflection and one for operation.
now
One
as you
for
can see this,
rotation.
okay, let's see if this forms a group or not. Okay, so consider R. So R is rotation. Let me concretely define it. Rotation by 2 pi by 3, and W is a rotation by minus 2 pi by 3. And I think rest all the other definitions are clear. Let's look at you said that whether this is a group or not. Let's choose two elements. Let us take R and let us take sigma, and we apply it on the equilateral triangle. Okay, so you will see that whatever result you will get, the same result can be reproduced if you apply sigma double prime on the equilateral triangle. That means R sigma. So under what is the group operation here? The group operation is multiplication because I'm multiplying the two operators and then making the two operators act on the equilateral triangle. So if I multiply R and sigma, I'm getting an element sigma double prime which belongs to the group G. So this is, I think, the closure property getting satisfied. Yes. Similarly, if you take R and multiply with itself and then make it act on the equilateral triangle, then whatever result you will get, the same result will be reproduced when you apply W on the equilateral triangle. That means that the operator R square belongs to G because R square is nothing but W. So similarly, you can check the closure property, associative property, inverse property, and the identity. I already included the identity element, which is E. But this is a non-abelian group.
Yes, it is not associated.
And how should I prove? I should have two elements from the group such that it is not equals to when I multiply in a reverse way. So let me give an example. So if you take R and sigma, you get sigma double prime. But if you do sigma and R, you get sigma prime. So you can see there are two elements here, R and sigma. that do not commute. Hence, our group is a discrete group because it has finite number of elements. How many elements? It had 6 elements. That's why it is a discrete group, and it's non-abelian because we found a particular case when the commutation relation is not satisfied. Okay.
Excuse me.
So Vikram, there is a software called as Handbrake.
Okay.
HANDBRAKE.
Okay.
The video, maybe you'll get 200 MB or something like that. Okay.
Okay.
So if you use Handbrake, it will make this 200 MB to somewhere near 40 MB.
Yes, here also, sir, same thing. I'm getting around
Okay.
45 to around 50 MB. The video will be.
Okay. So I think it can reduce it further.
Yeah.
This Handbrake can reduce it further, and the quality will stay same.
Okay. Is it paid version or sir free?
Free. It's an open source software.
Okay.
So it's fantastic. You can reduce big video sizes to very small without losing an inch of the video quality. An inch of video quality is not lost.
Okay.
Because all other things, they compromise with the